The atom's European social class. The evidence suggests that nuances of another particle in today's smasher, on different occasions, are more vital and twice as fundamental. It has detected 3 brand new particles that may be crucial in determining how we envision the universe and its future. Specialists at CERN have recently uncovered revelations that turn our understanding of the universe on its head. Beneath the surface of their fundamental experiments lies a staggering array of particles and forces so peculiar that they could completely defy expectations. These fragments represent diverse perspectives on particles that challenge the very foundation of reality. What dazzling, special secrets remain hidden? Could we, during these tests, unlock profound mysteries? Let's delve into the world of CERN and unravel the pieces of data that could redefine our universe. Could a wormhole speculatively appear out of nowhere due to the groundbreaking evaluations conducted at CERN's Large Hadron Collider, LHC? The LHC is the most significant and powerful particle smasher, located near Geneva, straddling the border between Switzerland and France. There are privileged secrets surrounding this extraordinary institution that the world remains unaware of, insider information that may revolutionize our understanding of material science. CERN, the European Organization for Nuclear Research, oversees projects of immense magnitude. This steady instrument extends over 27 kilometers and sits deep underground. The goal of the Large Hadron Collider is to grant physicists the ability to test various theories about the atom and materials science. It plays a critical role in advancing the standard model of particle physics, which helps us understand the fundamental building blocks of the universe. At its core, the LHC accelerates protons to nearly the speed of light before colliding them. These collisions produce showers of new particles, which scientists study to gain insights into nature's fundamental rules. It was through such experiments that the Higgs boson, often referred to as the God particle, was discovered in 2012. This breakthrough confirmed how particles acquire mass, marking a monumental moment in atomic physics. The experiments at the LHC are crucial for identifying characteristics that occur under extreme conditions, similar to those immediately after the Big Bang. The data collected from these collisions provide invaluable insights into the origins, evolution, and fundamental constituents of the universe. This makes the LHC instrumental in potentially uncovering new aspects of reality, including secrets surrounding dark matter and the fundamental forces of nature. High-level experimentation at CERN has sparked speculation about potential risks, such as the creation of miniature black holes or exotic matter that could pose a threat to Earth. However, CERN assures that all safety measures are met, with experts closely monitoring these experiments. Theoretical models confirm that any such risks are highly improbable. Through ongoing research and discoveries, CERN helps us better understand the universe, demonstrating the astonishing capabilities of human ingenuity and collaboration in the pursuit of knowledge. The LHC represents a modern scientific marvel, pushing the boundaries of what is known and challenging our perceptions of reality. The Hadron Collider, a technological marvel. The Large Hadron Collider, situated beneath the Swiss-French border, is an incredible feat of engineering. Spanning a 27-kilometer tunnel and reaching depths of up to 175 meters, it is the largest and most powerful particle collider in the world. It is a critical tool in the field of particle physics, designed to conduct experiments on an unprecedented scale. The main ring of the collider is housed in a tunnel that spans 3.8 meters in width, containing 2 parallel beam pipes. Each pipe directs protons in opposite directions, accelerating them with a series of superconducting magnets. These magnets are essential for maintaining the protons' paths, bending them at near-light speeds. Surrounding the beam pipes are layers of cooling systems, keeping the magnets at temperatures colder than outer space to ensure their optimal performance. The LHC operates with an extensive network of 1,232 dipole magnets to steer the beams and 392 quadrupole magnets to focus them with maximum precision. Each superconducting magnet is 15 meters long and weighs 35 tons, showcasing the sheer scale and ambition behind the collider. Unlocking the secrets of the universe. The primary objective of the LHC is to study the asymmetrical nature of the universe by observing the tiniest components of matter. By accelerating particles to nearly the speed of light and colliding them, the LHC allows physicists to analyze the resulting particles and gain deeper insights into the standard model of particle physics. One of the collider's key goals is to further investigate the Higgs boson. Its discovery in 2012 confirmed theories about how particles acquire mass. However, beyond the Higgs boson, the LHC also explores other fundamental forces and particles, addressing major questions such as the existence of dark matter and the nature of the universe shortly after the Big Bang. The LHC aims to verify the existence of new particles predicted by theoretical physics but not yet observed. These experiments are crucial for potentially discovering physics beyond the standard model, including supersymmetry and extra-dimensional perspectives. More than just a scientific endeavor, the LHC is a testament to global collaboration. Scientists from over 100 nations participate in its research, making it a symbol of international cooperation in the quest for knowledge. How does the LHC work? At the heart of CERN's research facilities, the LHC serves as a powerful tool for exploring the quantum realm. It enables scientists to observe and analyze the fundamental particles that make up everything in the universe. The collider accelerates two high-energy beams of protons inside ultra-high vacuum tubes, mimicking conditions similar to outer space. Superconducting electromagnets, cooled to temperatures below those of space, guide and focus these beams toward designated collision points. When the beams collide, they generate massive amounts of energy, producing a variety of subatomic particles, some of which exist only for fractions of a second. To capture and analyze these collisions, the LHC is equipped with massive detectors such as ATLAS, CMS, ALICE, and LHCb. These detectors gather data on the properties of the resulting particles, including their mass, charge, and momentum. This information allows physicists to test predictions of the standard model and explore the fundamental forces governing the universe. Groundbreaking discoveries. One of the most significant breakthroughs at the LHC was the discovery of the Higgs boson in 2012. This particle, often called the God particle, is crucial because it confirms the existence of the Higgs field, which grants mass to fundamental particles. The Higgs boson's discovery validated long-standing theoretical predictions and was a milestone in modern physics. Beyond the Higgs boson, the LHC has also uncovered various exotic particles. For example, it has provided evidence for pentaquarks and tetraquarks, particles composed of 5 and 4 quarks, respectively, which had never been observed before. These discoveries expand our understanding of hadronic matter, the substance made of quarks held together by the strong nuclear force. Pushing the boundaries of science. The discoveries made at the Large Hadron Collider, LHC, have already reshaped our understanding of particle physics, yet they are just the beginning. Scientists continue to push the boundaries of known physics, seeking answers to some of the universe's most perplexing mysteries. One of the most significant questions involves dark matter, an elusive substance believed to make up approximately 27% of the universe. While its presence has been inferred from gravitational effects on galaxies, dark matter has never been directly detected. The LHC's high-energy collisions may offer clues about its properties or reveal new particles that interact with it. Another major focus is antimatter, a mysterious counterpart to normal matter. According to current theories, the Big Bang should have created equal amounts of matter and antimatter. However, the observable universe is dominated by matter, with only tiny amounts of antimatter detected. Understanding this asymmetry is a key goal for CERN scientists, and experiments at the LHC could provide insights into why our universe exists in its current form. Additionally, researchers at CERN are investigating supersymmetry, SUSY, a theoretical framework that suggests every known particle has a heavier, unseen counterpart. If proven, supersymmetry could explain dark matter, unify the fundamental forces of nature, and expand the standard model. Although no evidence for supersymmetric particles has been found so far, upcoming LHC experiments may shed light on their existence. Exploring extra dimensions and the nature of reality. Beyond known physics, the LHC has the potential to explore even more speculative concepts, such as extra dimensions. Theoretical models, including string theory, propose that additional dimensions exist beyond the 3 spatial dimensions we perceive. If true, these hidden dimensions could explain gravity's weakness compared to other fundamental forces and provide a deeper understanding of the universe's structure. Physicists have also speculated that high-energy collisions at the LHC could produce microscopic black holes, tiny, short-lived versions of the cosmic giants found in space. While the idea may sound alarming, these black holes would be harmless, evaporating almost instantly. Their detection would provide groundbreaking evidence for extra dimensions and quantum gravity, offering a glimpse into the fundamental nature of spacetime itself. The future of the Large Hadron Collider. CERN continues to upgrade and enhance the capabilities of the LHC. The High-Luminosity Large Hadron Collider, HLLHC, scheduled to become operational in the late 2020s, will increase the collider's luminosity, allowing for even more particle collisions and higher precision measurements. This will improve the chances of discovering new particles and further refining our understanding of the fundamental forces. Beyond the HLLHC, CERN is already planning the Future Circular Collider, FCC, a next-generation particle accelerator that would dwarf the LHC in scale and energy output. With a planned circumference of 100 kilometers, the FCC could probe physics at unprecedented energy levels, unlocking mysteries beyond the reach of current technology. A global effort for scientific advancement. The success of the LHC is not just a triumph of European science, it represents a global collaboration. Scientists, engineers, and researchers from over 100 countries contribute to CERN's experiments, sharing knowledge and technology for the advancement of humanity. The discoveries made at CERN influence multiple fields, from medical imaging and radiation therapy to advancements in computing and artificial intelligence. The World Wide Web, initially developed at CERN to facilitate scientific collaboration, is a prime example of how fundamental research can lead to revolutionary innovations. Conclusion: a new era of discovery. The Large Hadron Collider is more than just an advanced scientific instrument, it is a gateway to the unknown. By recreating conditions similar to those of the early universe, it allows scientists to test theories, explore new physics, and challenge our understanding of reality itself. From the discovery of the Higgs boson to the search for dark matter and extra dimensions, the LHC has already changed the course of modern physics. With future upgrades and new experiments on the horizon, CERN's research will continue to push the boundaries of human knowledge, opening the door to discoveries that could reshape our understanding of the cosmos. As we stand at the frontier of science, one thing remains certain: the journey of discovery is far from over. The mysteries of the universe await, and the Large Hadron Collider will continue to serve as our most powerful tool for unlocking their secrets. Opening up brand new research horizons, particularly in physics, provides behavioral clues about matter under extreme conditions, like those shortly after the Big Bang. Theoretical dangers, such as strangelets and black holes, are smaller than anticipated and have been subjects of public interest and continued assessment. Strangelets are a more theoretical form of matter, believed to be more stable than normal matter. The theory hints at the potential for strangelets to convert any matter they come into contact with into strange matter. The apprehension surrounding this theory is that if strangelets were generated by collisions between particles at the Large Hadron Collider, LHC, they might trigger a catastrophic chain reaction, converting all matter on Earth into strange matter. However, extensive assessments and safety evaluations conducted by CERN and the global academic community have addressed these concerns. Studies have shown that even if strangelets did exist and were created in the LHC, they would most likely be extremely unstable and decay too quickly to cause any significant change to Earth's matter. Additionally, high-energy cosmic rays continually hit the Earth with energy levels far higher than those produced by the LHC without producing any strangelets. This natural evaluation suggests that strangelets are not a realistic threat. The concern that the LHC might create tiny black holes stems from speculation regarding additional dimensions in physics. Some theoretical models suggest that high-energy collisions within the LHC could create small black holes that would evaporate in an instant due to a process called Hawking radiation, named after physicist Stephen Hawking. Researchers concur that if small black holes were ever created at the LHC, they would not pose any risk. First, black holes created this way would be extremely small and fleeting, vanishing before they could interact with surrounding matter. Second, while the energies associated with LHC collisions are large by human standards, they are still far lower than the tremendous cosmic ray collisions that occur naturally. Since no dangerous small-scale black holes have been observed from cosmic ray interactions, it is highly unlikely that the LHC would produce any dangerous outcomes. CERN, along with independent review boards, conducts rigorous safety reviews to ensure that the experiments conducted at the LHC pose no risk to humanity or the planet. These reviews combine theoretical assessments, test data, and safety protocols to address any potential risks. While the LHC's experiments continue to push the boundaries of material science, they are carried out with a high degree of responsibility and scientific oversight. This guarantees that humanity will gain from groundbreaking discoveries without facing undue risks. Theoretical gambles often sound more like science fiction than plausible scientific outcomes. However, a thorough evaluation of potential risks suggests that the experiments at the LHC are safe and that any risks are negligible. One of CERN's most interesting and extraordinary proposed experiments involves the search for magnetic monopoles. A hypothetical particle, a monopole is a magnet that has only one pole, either a north pole or a south pole. In contrast, regular magnets normally have both north and south poles. The existence of magnetic monopoles was predicted by physicist Paul Dirac in 1931, who demonstrated that their existence would explain why electric charge is quantized, meaning it always appears in specific quantities. Despite their theoretical significance, magnetic monopoles have never been observed. At the LHC, experts have been searching for evidence of these elusive particles. If magnetic monopoles were ever detected, they would revolutionize our understanding of magnetic fields and could lead to significant advances in technology, including new methods of energy storage and transmission. In addition, the discovery of magnetic monopoles would provide experimental evidence for grand unified theories and string theories, which attempt to unify all fundamental forces of nature into a single framework. While the search for magnetic monopoles may seem esoteric, it embodies the essence of scientific research and curiosity that drives legitimate inquiry at CERN. The pursuit of such captivating and potentially groundbreaking particles reflects the organization's commitment to exploring the unknown and pushing the boundaries of human knowledge. Another fascinating investigation at the LHC involves the possible existence of particles that could travel faster than the speed of light. According to Einstein's theory of relativity, the speed of light is the ultimate speed limit in the universe. However, some theoretical models suggest that particles called tachyons could exist, which would always move faster than light. Detecting tachyons would challenge our comprehension of spacetime. While most physicists remain skeptical about their existence, the search for such particles at the LHC demonstrates CERN's openness to exploring even the most speculative corners of theoretical physics. The LHC also enables scientists to carry out experiments that reproduce the conditions of the early universe, shortly after the Big Bang. These high-energy collisions create a state of matter referred to as quark-gluon plasma, which existed only minutes after the Big Bang. By studying this plasma, physicists hope to better understand how the universe transitioned from its fundamental high-energy state into the complex and organized universe we observe today. In summary, the various experiments at CERN, from searching for magnetic monopoles to creating quark-gluon plasma, highlight the depth and breadth of the serious research conducted at the LHC. They demonstrate that CERN is pushing the boundaries of our understanding of the universe and exploring new areas of physics that were once considered purely speculative. The ultimate objective of the LHC is to expand human knowledge, unlocking profound insights about the universe. By smashing particles at extraordinary energies, researchers can explore the very nature of matter and the fundamental forces governing the cosmos. This remarkable journey for understanding mirrors humanity's innate curiosity and our desire to explore the unknown. The revelations made at the LHC have profound implications for our understanding of the universe and our place within it. The search for dark matter and dark energy. One of the most profound mysteries in modern physics is the nature of dark matter and dark energy. While ordinary matter, the kind we can see and interact with, makes up only about 5% of the universe, dark matter is believed to account for around 27%, while dark energy constitutes nearly 68%. Despite its dominance, dark matter has never been directly detected. Scientists only infer its existence from gravitational effects on galaxies and cosmic structures. At the LHC, researchers are searching for hypothetical particles that could be responsible for dark matter. One of the strongest candidates is the weakly interacting massive particle, WIMP. If WIMPs exist, they could be produced in high-energy collisions within the LHC, leaving detectable signatures in the data. Another possibility is that dark matter consists of actions, hypothetical particles that could solve certain inconsistencies in quantum physics while also explaining dark matter's gravitational effects. If scientists succeed in detecting dark matter particles at the LHC, it would be one of the most significant discoveries in modern physics, reshaping our understanding of the universe's structure and evolution. Probing extra dimensions and the nature of gravity. Another major area of exploration at CERN is the possibility of extra dimensions beyond the three spatial dimensions we experience daily. Theoretical models, such as string theory, suggest that additional dimensions may exist, but they are hidden from our perception. One way to test this idea is by studying how gravity behaves at very small scales. Unlike the other fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, gravity is vastly weaker. Some theories propose that this weakness is due to gravity leaking into extra dimensions. If true, the LHC could provide indirect evidence for these hidden dimensions by observing unusual particle interactions or missing energy signatures in experiments. Discovering extra dimensions would revolutionize physics, potentially offering new insights into unifying all forces of nature into a single, elegant framework. Antimatter and the matter-antimatter asymmetry. One of the greatest unsolved mysteries in cosmology is why the universe is made almost entirely of matter, despite the fact that, according to theory, the Big Bang should have produced equal amounts of matter and antimatter. If matter and antimatter had been created in equal amounts, they should have annihilated each other completely, leaving behind only energy. Yet, our universe is filled with galaxies, stars, and planets, all made of matter. To investigate this asymmetry, CERN operates the antimatter factory, where researchers create and study antimatter particles, such as antiprotons and antihydrogen atoms. By comparing the properties of matter and antimatter, scientists hope to uncover subtle differences that might explain why the universe evolved with an excess of matter. Future of high-energy physics, the next-generation colliders. While the LHC has already led to groundbreaking discoveries, most notably the Higgs boson in 2012, physicists are now looking toward the future of particle acceleration. Proposals for next-generation colliders include the Future Circular Collider, FCC, a proposed successor to the LHC, designed to be much larger and capable of reaching even higher energy levels. It could provide deeper insights into the Higgs boson and dark matter. The International Linear Collider, ILC, a planned linear accelerator that would allow for more precise studies of fundamental particles, especially the Higgs boson. Muon colliders. These would use short-lived particles called muons to achieve even higher energy densities in collisions, offering new possibilities for exploring unknown physics. The broader impact of CERN's work. Beyond theoretical physics, CERN's work has had significant real-world applications. The research conducted at CERN has led to advancements in medical imaging, cancer treatment, such as proton therapy, and even computing. The World Wide Web itself was invented at CERN in 1989 by Tim Berners-Lee as a way to share research data among scientists worldwide. As experiments continue, CERN remains at the forefront of scientific discovery, pushing the boundaries of human knowledge and inspiring future generations of researchers.